I am going to turn this over to Silvio Cesare, who will be delivering the next talk for you.
Hello, thank you for attending this presentation. Little story, I arrived in Vegas yesterday at about 10 a.m., 11 a.m. Coming from Australia. It took about 24 hours in flights and travelling time. Unfortunately, my luggage didn't arrive with me, so I had to buy a couple of shirts last night from the Caesar Forum shops, and I'm still wearing my jeans and sneakers, if you're wondering, from the flight, so excuse me for that, but my luggage should arrive tonight, hopefully. So this talk is about bugalize.com, detecting bugs using decompilation and data flow analysis. A little bit about who I am and where this talk comes from. I'm a PhD student at Deakin University. My thesis is currently under examination, so hopefully soon I'll progress and be awarded that degree. I'm also a book author. The title of my thesis was Software Similarity and Classification, and I've written a book with the same title of that. If you go to my website, there's a free preprint of that book available as well. And this talk covers some of that PhD research. I've also looked at other things in the past, such as malware detection, and there's a lot of overlap between this work as well. The same engine that I use to do malware analysis is used to do the static analysis and decompilation in this work. I'm also a bit of a hobbyist. This is my Linux and Arduino powered home gardening system. The irrigation system is controlled by my Linux box that has a cron job starting and stopping the irrigation. So detecting bugs in binaries is useful. We know that static analysis can have its uses and is beneficial in many respects, but in most cases you need access to the source code. But if you look at things like penetration testing, you often don't have that source code available. So we need an approach to do black box testing. So detecting bugs in binaries is useful in that case. External auditing and compliance is also another valid reason for why we should have some assurance on our software. And assurance of software can't really be guaranteed once we've compiled and linked a particular program. We can do source code analysis, but that process of compiling and linking converts that source code into a binary, and to verify that that compilation and linkage has performed successfully and not introduced new errors, we need to have an approach to detect bugs in binaries. Finally, if we have third-party software, we might be using a library or a product from a vendor who doesn't provide source code. Having some assurance of the quality of that software, that it doesn't have really big bugs in it that can be easily detected by an adversary, is something of benefit as well. So the work that I'm doing today and that I'm presenting about today has a number of, I suppose, innovations, and that's certainly how we describe it in the academic sense. The innovation is really performing static analysis on binaries by using decompilation and then using data flow analysis on those results to find bugs. The novelty is in combining that decompilation with traditional static analysis techniques. So we've got a whole range of static analysis techniques that apply to source code, and if we introduce decompilation, we can use those results that have been done before. There are a number of methods to analyse programs formally. We have the main approaches include theorem proving. So you might have things like defining the semantics of a program using mathematical representations, and then proving properties based on those semantics. Typical semantics used for verification include axiomatic semantics. There are also other semantics possible, denotational semantics, operational semantics, and so forth. Another approach to formally proving the correctness or verifying programs is via abstract interpretation. And abstract interpretation essentially abstracts the running of a program and reduces the complexity of looking at concrete execution. And certainly, according to Rice's theorem, you can't precisely prove specific properties of a program, but using abstract interpretation makes that possible through approximation. A classic example that is used to describe how abstract interpretation is using the abstract domain of signs. In this particular case, you abstract the data of particular variables by representing it using the sign of the variable. So you might have positive, negative, and zero, and you can prove certain properties of the program, such as particular variables are never zero or always greater than zero, and so forth. Another approach to formally proving program correctness is model checking. And model checking essentially represents the states of a program, and you verify that your model of a program corresponds to its specification. So the outline of this talk that I'm going to give today covers a number of things. I'll talk about decompilation, then I'll talk about data flow analysis. I'll talk about optimizations on the intermediate language that I use to represent programs using that data flow analysis and decompilation. I'll talk about bug detection. I'll talk about the system that I've implemented bug-wise, and finally I'll talk about future work and conclude the presentation. But before I get into the actual analyses that I'm using, I need to sort of cover some of the terminology of program analysis, and in particular, talking about the control flow of a program. For some of you, you might already know this. This isn't really new work. It's just, looking at some of the terminology. So a control flow graph represents control flow within a procedure. And control flow describes the possible flow of execution within a program statically. A control flow graph is a directed graph. Each node in the control flow graph represents a basic block, and a basic block represents a sequence of instructions without an intervening control flow transfer instruction. An edge between those basic blocks represents that a branch or control flow may be taken via that edge. Control flow graphs are typically used for intra-procedural analysis, that is, analysis within a procedure. And there are a number of types of analyses that can be performed intra-procedurally, specifically flow-sensitive analysis and flow-insensitive analysis. Flow-sensitive analysis takes control flow into account. So we're taking into account that specific paths may or may not be, exist in that control flow graph. Examples of analyses that don't take control flow into account are things like pointer analysis, where you can specify a set of logical formula to represent that. In contrast to the control flow graph is a call graph. A call graph represents the control flow between procedures. Again, a call graph or a function call graph is the directed graph. Each node in the graph represents a procedure, and each edge in that call graph represents that the source of the edge, that procedure may call the destination of that edge. So call graphs represent interprocedural analysis, and they look at the analysis between procedures. In interprocedural analysis, you have context-sensitive and context-insensitive analyses. A context-sensitive analysis takes into account the call stack of each function. Specifically, at each particular function, you can have a certain set of call stacks that may exist. A context-insensitive analysis doesn't take that into account, and it's not as precise as a context-sensitive analysis. So that's sort of the terminology that I'm going to discuss. Now onto the sort of the meat of the presentation, or at least the first part of it, which is about decompilation. So decompilation essentially recovers source-level information from a binary. I don't actually use the textual source code representation of a binary to do my bug detection, but I do use some high-level information that is obtained through decompilation. So the basic approach that this work takes, that Bugwise takes, is to represent x86 assembly language with an intermediate language. An intermediate language makes the analyses easier, and I'll talk about that in some later slides. I infer stack pointers, and from that I can decompile local variables that are based on the stack, and also procedure arguments which are based on the stack. And that is effectively the part of decompilation that I'm using, recovering local variables and procedure arguments. So the intermediate language that I use is called wire, and it's a formal intermediate language for binary analysis. Why do we have an intermediate language? Why don't we perform analyses directly on x86? Well, x86 is complex and big. As a CISC instruction set, it has hundreds of possible instructions with many addressing modes. It's useful to have an intermediate language that is more concise, that is more risk-based, because you have to implement less handlers for each instruction that you're working with. So wire is a low-level RISC-style assembly language, very simple addressing modes. It's register-based. The memory model includes virtual memory of the 32-bit address space, and this is a result of translating x86 to this language. It's very similar to Halvar Flake's Rail language. Like Rail, I transform one x86 instruction to one or more instructions in the wire language. Wire also has formally defined operational semantics. I talked a little bit earlier of some of the approaches of proving program correctness using formal methods. Operational semantics describe effectively how a particular instruction transforms the state of the machine. One of the things that we can do with the formally defined language and formally defined operational semantics is prove particular program properties about those things. So on the left, I've got some code, and on the right, I've got some code also equivalent to that, but that has been obfuscated using dead code insertion. So using operational semantics, we can formally prove that the unobfuscated sequence of instructions is equivalent to our obfuscated version. But, you know, the formal verification about proving equivalence between obfuscated and non-obfuscated programs and instructions is not really the focus of this work. This work is all about detecting bugs in binaries. And to do that, like I said, you need to perform decompilation and recover local variables and arguments. The first part of that process is recovering stack pointer information within each procedure. This approach has been proposed earlier in the Hexrays decompiler, and that's what Hexrays uses, and IDAPRO as well actually, uses to look at stack-based variables. The basic presumption is that within a procedure, at the start and end of each basic block, the stack pointer relative to the beginning of the procedure is constant. It's not always true, but when you transform a high-level language and compile it into assembly code, this is pretty much the case in most times. So we determine what this stack pointer is relative to the beginning of the procedure by representing it using linear inequalities. So we know, for example, that the stack pointer at the beginning of the procedure is 0. The stack pointer at the exit point of the procedure is 0. And we also know that particular types of instructions modify the stack. Calls modify the stack, pushes and pops modify the stack, and we can represent these mathematically. And we solve this using a standard off-the-shelf solver for linear inequalities. Specifically, it uses a simplex algorithm to solve this. So once we've determined what the stack pointer is throughout each procedure, we can then go on to the next stage, which is recovering local variables and procedure arguments. So it is based on that stack pointer inference. And the way that we use this is that when you reference a local variable or a stack-based variable, you typically reference it relative to the stack pointer or the frame pointer. And if we know what that stack pointer and frame pointer is at particular points in the program, we have these static offsets into our stack space that represent local variables and procedure arguments. So on the left, I've shown the wire intermediate language representation of some code. And on the right, I've performed that local variable recovery and it simplified it by quite a significant degree. And in fact, that code on the left simplifies to a free of a local variable. And that's important because later on we'll be looking at things like double frees and use after frees and representing these stack-based variables using native registers and native variables in the intermediate language makes this problem solvable. So again, procedure parameter and argument recovery is very similar to the local variable recovery. It's based on stack pointer inference. Again, we know whether it's a local variable or an argument based on its position relative to the stack pointer or the frame pointer. Now, there are different call conventions that can be used, and that stack pointer inference takes into account that different call conventions can be used, such as call it cleans up or call e cleans up. But sometimes when we have, in particular, call conventions, a register might be used as an argument. We can detect that a register is an argument by looking at its liveness in that procedure. So a live variable is a variable that will subsequently be read before it is redefined. So any register that is going to be used at the beginning of a procedure before it's defined or redefined is a procedure argument. It could also indicate that it's an uninitialized variable, but in this case we'll look at it as a procedure argument. Okay, so that's the decompilation that this work uses. The next component of the system is data flow analysis. So taking that intermediate language, those recovered variables that are now native registers in that language, and performing data flow analysis to determine specific types of bugs and problems that can exist. So data flow analysis, or DFA, reasons about data. Data flow analysis should be conservative. When we say it's conservative, it means that the data should be over-approximated but never under-approximated. So you may have false positives, but you shouldn't have false negatives. Data flow analysis is what optimizing compilers use. So data flow analysis is performed to determine specific properties of the data within the program, and when certain properties are true, certain optimizations can be applied. The types of data flow analysis that a compiler uses include things like reaching definitions, upwards exposed uses, live variables, reaching copies, and so forth. There's quite a large number of data flow analyses that are possible. And the work that Bugwise uses, the analyses that Bugwise uses use def type data flow problems, so reaching definitions, upwards exposed uses, and live variables. I'll talk a little bit about that shortly, but that's the type of data flow analysis that I'm talking about when I'm giving this presentation. So we have this, this general concept of we need to represent the data in a program, but how do we, precisely model that problem? What we can do is we can represent data entering and leaving a basic block, and that's what we're looking at when we represent this data flow problem. So we can set up a number of equations that mathematically represent the flow of data within a procedure, and we'll model what each basic block has for data. So we have data entering or leaving a basic block, and we have a transfer function that takes the data entering that basic block, modifies it in some way according to the instructions in the basic block, and that gives us the data leaving the basic block. We also have to look at control flow, because there are different paths in a program, and depending on what path you're taking, the data can be modified accordingly. So we have a concept of a join operator that combines the predecessors of a basic block in a control flow graph, or a flow graph in general. Depending on the types of analysis that we're doing, whether it's a forward analysis or a backward analysis, you have the concept of joining the predecessors of a basic block, or joining the successors of a basic block. So the first example that I'm going to give as a data flow problem is a reaching definition. Now, a reaching definition is a definition of a variable that reaches a program point without being redefined. So if we look at our control flow graph, or our flow graph that I've shown, the bottom node has print x, what are the definitions that reach that point? So we have at the top y equals 3 and x equals 1. They both reach that point, but we have that x equals 2 can also reach that point because there are two paths where x is modified which reach that final node. So we include all of those definitions in our reaching definition analysis. Okay, so that's a reaching definition, and we've got sort of a model of how we represent data flow problems. But how do we, what's a simpler way of representing data flow problems for the types of analyses that we find useful? And this is a type of framework that most compilers use. Generally, there's forwards and backwards analysis, depending on whether we start at the beginning of a procedure and work our way to the end nodes, or we start at the end nodes and work our way back upwards. So we have a forwards and backwards analysis. We have initialization of our data entering a basic block, our in, our data leaving the basic block out, and we also have a concept of gen and kill sets for each basic block, and we can use those in our transfer function, which describes how the data is modified by a basic block. So that's our definition of our transfer function, and this is very commonly used to solve problems like reaching definitions, live variables, and so forth. Our join operator that I talked about earlier in that representation, in this particular framework, can be either a union or an intersection of sets. So, looking at our reaching definitions problem, we have, we know what the basic, idea of a reaching definition is. The definition that can potentially reach a particular node or point in the program, and we can represent this using our framework that I just described in the last slide. So we have our gen set, which is the definitions that appear in that basic block and reach the end of the basic block. We have our kill set, which is all definitions that never reach the end of the basic block. We can initialize the data leaving the basic block, and we have a join operator based on union. And because it's a forward analysis, we look at the union of the predecessors of that basic block. Another type of data flow problem, which is really the opposite of reaching definitions, is upward exposed uses. And this tells us the uses of a definition. So at a particular program point, we might want to know when that data will be used. And we have our gen and kill sets defined accordingly. Initialization, again, we have our confluence operator or our join operator is union, and because it's a backward analysis, we look at the successors of the basic block and not the predecessors. There are many more data flow problems. Probably the last one that of real note is live variables. And a live variable is live if it will subsequently be read without being redefined. And that's used in things like dead code elimination. We also have reaching copies, which tell us the reach of a copy statement or an assignment of a particular variable. But as I said, there are more data flow problems out there. There's available expressions, very busy expressions, and optimizing compilers use an entire range of data flow analyses and problems to perform their optimizations. So we represent our data flow problem using this framework of gen and kill sets. But how do we actually solve this data flow problem? We can initialize it. We have a way of joining control flow with predecessors and successors. We have transfer functions. How do we come up with the final result of data entering and leaving each basic block? Well, there's an iterative solution to this. We initialize our sets of data. We apply the transfer function. We apply the join function, and we iterate over all these nodes in our control flow graph, and we just repeat that until our solution stabilizes. That is, until it reaches a fixed point. And that's effectively why they call these things monotone frameworks and monotone analysis, because our data will always increase or always decrease until it stabilizes and reaches a fixed point. And we have to have certain properties in our data flow representation to ensure that it is a monotone data flow problem. But effectively, for all the data flow problems that we're going to look at, we can guarantee that they do reach a fixed point. So that's the iterative solution to solving data flow problems. There are other ways of representing data flow problems, though, and solving data flow problems. probably the biggest different approach is by using logic. Datalog is a very popular language and framework to solve these types of logic problems, and it's a syntactic subset of Prolog. So we represent our reaching definitions problem, as I've shown here, using Datalog statements and logical formulae. We can represent these, and then we can solve these with the Datalog solver. Typically, representing problems with logic is simpler than representing them with that gen and kill, with that monotone framework that I talked about earlier. So I've talked all about the intraprocedural way of solving data flow problems, but it would be really useful if we could solve data flow problems interprocedurally as well. And we can do this using our framework by joining our control flow graphs for each procedure into what's known as an interprocedural control flow graph. And this effectively takes each control flow graph and joins them into one supergraph. We replace calls in each control flow graph with a branch to the control flow graph that it's calling. We replace returns from functions with branches back to the call site. And then once we have this supergraph, we can apply a monotone analysis that I just explained. So that's the data flow analysis. That's the theory part of working with data flow problems and using compiler-style data flow analysis as the basis for bug detection. The final sort of, precursor to looking at bug detection is looking at the optimizations that are performed on the wire intermediate language using the data flow problems that I've just described. So, as I said, the optimizations are required to perform other types of analyses. So the decompilation, the stack pointer inference, requires optimization on the intermediate language for the process to work correctly. And also the bug detection requires the optimization process. The optimization reduces the size of the intermediate language code, and the optimizations are based on data flow analysis. So the optimizations that I'm using in Bugwise include constant folding and propagation, copy propagation, backwards copy propagation, dead code elimination, and there are other types of optimizations that are out there, but these are the primary ones that I use in Bugwise. So the first optimization to look at is constant folding. And the motivation for this is to replace instructions such as x equals 5 plus 5 into x equals 10. It's pretty intuitive that 5 plus 5 can be folded or combined into a single constant. And the way that we do this is for each arithmetic operator, if the reaching definition of each operand is a single constant assignment, then we can fold the constants in the instruction. Constant propagation has a motivation of reducing the number of assignments in a program. So on our left, we have x equals 34, and that value of x can be propagated into the next instruction, giving us r equals 34 plus y. So to solve this, to perform this optimization, if all the reaching definitions of a variable have the same assignment and it is constant, the constant can be propagated to the variable. Copy propagation reduces the number of copies in a program. So on our left we have y equals x, and that can be propagated into a later instruction. We can solve this in a couple of ways. Probably the easiest way to describe this is by looking at reaching copies, a data flow problem that I mentioned briefly earlier. A reaching copy tells us the reach of a copy statement. And at each use of x, where x equals y, if it's a reaching copy, replace x with y. And that's effectively how we use data flow to perform these types of optimizations. We know specific properties of the data are true, and we can look at them, and we know when we can apply these optimizations. Backwards copy propagation is similar to copy propagation in motivation. It's to reduce the number of copies. In Bugwise, both forwards and backwards copy propagation are required for the system to work effectively. Dead code elimination or dead store elimination is probably the optimization that most people have heard of. And the motivation of this is to reduce the number of instructions in a program. To perform dead code elimination, you need to know about the liveness of a variable. And remember that a variable is live if it will be read or used before it is redefined or defined absolutely. So for any definition of a variable, if the variable is not live, then eliminate the instruction. So on our left we have x equals 34, and that x equals 34 is never going to be read again because in the next instruction x is redefined to be the value of 10. So we know that x equals 34, x is not live, so we can eliminate that instruction. So that's pretty much all the necessary groundwork to perform bug detection. So the overview, the process of detecting bugs in binaries, we decompile the program, transforming local variables into native intermediate language variables or registers. We use data flow analysis to reason about those variables in our intermediate language when those variables are used and defined. And then we can detect particular types of bugs. So the types of bugs that I'm detecting, are not really that impressive, but for this work, they're reasonably adequate. So we're going to look at an old school bug here, buffer overflows caused by passing the results of getEnv to a string copy or something equivalent. We're going to look at use after freeze and double freeze. So this doesn't detect all possible cases of these bugs, but it detects specific cases with specific properties true. So the getEnv bug we're going to look at is detecting unsafe applications of getEnv. So a classic example is a string copy, the results of getEnv, which gets an environment variable from Linux, copies it directly to the buffer without any bounds checking. Sometimes you can have bounds checking and have this code present at the same time, but in most cases, if you pass getEnv directly to a string, it typically indicates that there's a bug. So the way that we detect that this bug exists, for each time getEnv occurs in our program, if the return value of that function is live, that is, the results of the results of that environment variable returned from getEnv are going to be used, and that result is the reaching definition to the second argument of a string copy or a string concatenation, then we make a warning. A very simple approach using data flow analysis that is able to find bugs. And this is a very old school bug, so 2001, hello. To detect use after free bugs, for each time a free of a pointer occurs, if that pointer is live, if that pointer will be used before it is redefined, then we warn on that. For a double free, for each time a free of a pointer occurs, if an upward exposed use of pointer, that is where the variable is used, is free pointer, then we warn. And by the way, 2001 wants its bugs back. So that's the bug detection approach using data flow analysis that I'm using. The next part of the talk looks at the results obtained and the system implemented. So this is based on some previous work that I've been working on for quite a while now, a number of years. I did my master's on a malware detection system, and also during my PhD I've worked on that as well. It's quite a lot of code, about 100,000 lines of code. It's a framework for static analysis, binary analysis and so forth. And bug-wise, this particular work is built as a set of loadable modules to that malware system. Everything in this talk and more is implemented, so there isn't anything that I've talked about that hasn't been implemented in this system. So for that getEnv bug that I was talking about, I scanned the entire Debian 7 unstable repository. Debian 7 is stable now, but when I performed this work, Debian 7 was still unstable. There were about 123,000 ELF binaries. About 30,000 of them couldn't be scanned for various reasons, primarily not supporting particular file formats and shared libraries and whatnot. The system reported 85 bugs across 47 packages, and those are the packages that have been reported as having buffer overflows as a result of unbounded getEnv copying. Not all of these are strictly bugs. Some of them have been false positives when you have bounds checking in conjunction with a reasonably unsafe or, not a very good use of string copy and get ends together. Some interesting data. I'd say about 80% are true. Not all of them are true positives. And I haven't reported all of these to Debian as well. It's still a work in progress. But generally, I think, even though that not all of them are true positives, I think the use of that code snippet is generally sort of ill-advised. I don't think it's a great idea, to use that type of model of working with getenv. Some interesting data. Looking at the ELF binary sizes and how they exist in the Debian repository. It's pretty much linear growth with logarithmic scaling, plus there are some outliers. This is sort of interesting to know because when we look at the scalability of scanning for binaries, if we have linear scaling of our binary analysis framework, we can make some estimations on how well we can scale across the entire repository of software that we're looking at. I looked at the getenv bugs over time sorted by binary size. Now, what we're looking at here is wondering, do we have more bugs if we have bigger binaries? And if that is the case, then we should expect a non-linear growth over time looking at new packages. And in fact, it's sort of a cross between a linear growth or a power growth. There's a very slight difference between linear and power growth. So what we can say is that there's not a real significant increase in the number of bugs as packages get bigger. Some statistics about those getenv bugs. The probability of a binary... sorry.
Number of bugs is an absolute or number of bugs per meg?
So looking at the presence of does any bug exist given a larger binary size? So the general thing that I'm looking at, do we have more bugs in software as it gets bigger? But I think with getenv, developers either make that bug or they don't make that bug. So as the binary gets bigger, if they know that this bug class exists, then they're not likely. They either do or they don't. So the probability of one particular binary in Debian being vulnerable is quite low, 0.00067. The probability of a package being vulnerable is a bit higher because each package consists of a number of binaries. Now the probability of a package having a second vulnerability, given that one binary in the package is vulnerable, is quite high. So we know that if a developer implements software with this particular type of bug, they're more likely to write more software with the same bug. It seems pretty obvious, but it's nice to represent this with some statistics as well. This is a double free found in a set group ID game program in Debian 6. It has been fixed after I reported it, but it shows that it is able to find bugs in real software. And this was done when I was scanning all the set user ID and set group ID programs in Debian 6 at the time. So we can see that free full name has a path to a double free if a file open fails, which is quite unlikely in this case, which is why it hasn't really triggered any crashes in the past. Bugalize.com is a web service and a website where you can submit samples and Linux executables and get fairly close, fairly fast scan times and results shown in your web browser. So these are some of the types of reports that it generates. On the top diagram is a double free that's been detected, and it tells you the EIP or the program counter of each particular free that causes the problem. On the bottom is a buffer overflow caused by that getenv problem And these are real binaries in Debian that it's worked on. To support this web service, I built some infrastructure using Amazon. The scanning of each binary is actually performed on a cluster of Amazon servers. There's about 3 servers running at the moment. And jobs are distributed to each scan server via a web load balancer. There's also a lot of other supporting infrastructure on Amazon, such as DNS, reporting, logs, and so forth. This also shares work with my other services, including Sincere, which is a malware similarity service, and CloneWise, which is a software, a tool to detect embedded copies of well-used libraries. So that's pretty much all the things that I'm going to talk about today. I've described how to decompile programs, how to perform data flow analysis, how to use compiler-style optimizations on intermediate code to get simpler representations, and how to represent bug classes using data flow analysis, and finally talking about a system that implements what I've talked about today and that has found bugs in binaries. In the future, I'd like to improve the core of the engine a little bit. I'd like to look more at interprocedural optimization, which will be able to detect a larger number of bugs when we have use after freeze and double freeze occurring that require interprocedural analysis because they consume more than one procedure. Well, I'd also like to look at pointer analyses, which would improve the precision of the system. And I'd like to improve the decompiler. The decompiler is okay, but it's not perfect at this point, and there's still a number of cases where it doesn't perform as effective as it should. I'd like to improve the bug detection components of the system, looking at things like uninitialized variables, unchecked return values, and I'd finally like to look at more evaluation, performing more evaluations and get more results. I haven't presented any really big bugs, but it's a framework that can detect bugs and has found bugs in sort of the low-hanging fruit category of software. And certainly as a quality assurance tool, it's met its goal of finding bugs across an entire repository of software. So in conclusion, traditional static analysis can find bugs, and decompilation bridges the binary gap. We can apply all those traditional static analysis techniques, well, not all of them, but a large proportion of them, by decompiling our software first. Bugwise works on real Linux binaries, and it's available to use. It's free to use. You just have to go to my website. So thank you very much. Are there any questions?
So what would it take to use this on non-Linux binaries? So what's the initiative?
So the system actually works pretty effectively on Windows. It has a P32 parser. The x86 is parsed pretty well. I think the only reason I chose Linux in this work is that I was more familiar with the simple types of bugs that I was looking at. Certainly, I think it can be applied to Windows, and the back end does support it. Although, publicly it's not. You have to submit ELF binaries, but certainly the intermediate language and the object file parsing, the decompilation, all works on Windows binaries as well. But then again, you have C++, which increases the complexity as well. So.
So it's available for use as a black box right now that I can see things in. What if I want to change which functions it actually uses instead of string?
The question was, sorry for not repeating the questions earlier. The question was, the system acts like a bit of a black box. How can I customize that system and put functions that I want to look at? It is true, it is a black box at the moment, and I'm not quite sure if I'm going to open it up more. Certainly it's something that I may consider, like making it more customizable, putting functions to look at, representing data flow analysis and specific ways of customizing that. But at this point in time, I don't have plans for that. So, it's not great for everyone, but as a free service, I think it's quite reasonable.
Another question was, wire is a custom IR. It seems like everybody makes their own IR. What is wire giving me that someone else is giving to other people?
So the question was, why have I used my own intermediate representation, why haven't I used something like LLVM, and used something like Clang or something to do static analysis? I think I developed Wire a number of years ago. Also, there's Rail, which is probably the closest thing to it. I developed Wire a number of years ago, before there was sort of a plethora of IRs and ILs available to use. One of the main advantages that my intermediate language has, and what I designed it for, was it's pretty fast to do the translation. So when I look at malware classification, I can do pretty much close to real-time analysis, and that is based on having a pretty fast translation. So that is the main advantage of it. If I did it all again, I probably would go to a more established intermediate representation and intermediate language. Certainly LLVM is something that would open up more possibilities. There are also other advantages of using my own intermediate representation. Some of the decompilation primitives are represented in that intermediate language, which makes the analysis a bit easier for the specific problems that I'm looking at. But maybe a bridge to that is by having a transformation from my intermediate representation to LLVM, and then using sort of existing code based on LLVM around that. Does that reasonably answer your question?
Yeah, but I wasn't even thinking of established things like LLVM. I was thinking academics have things called chain tracing or bitcoins and so forth.
BAP and Vine weren't available. BAP and Vine weren't available at the time that I developed this, so I think Vine.
Is that a PhD editor right now? I know that was available like 6 years ago as well.
Well, Vine, I think, was released maybe a couple of years ago as part of the BitBlaze framework, and BAP has been a more recent release after that. When I developed the original system, I think BitBlaze was entirely closed, and there was certainly no public implementation of that system at the time. And Vine is effectively, as far as I know, an extension of Vex, which comes from the Valgrind IR. But Vex at that time didn't really suit my needs. But it's if I did it all again, maybe BAP is the way to go now. But certainly at the time that I developed the system, Vine wasn't public, which is the predecessor to BAP.
How much did you have to tweak the decompiler for GCC, because you're looking at Linux binaries, and how much would you have to, or have you tweaked it for other compilers like CL?
I think that's a reasonable question. I mean, the analyses are fairly, robust. The decompiler is fairly reasonable. I can't say I've got an enormous amount of first-hand commentary about that, but certainly the analyses are defined so that if you use the common call conventions, then it should be able to get something out of it. So, and there's only sort of a reasonable amount of finite sort of call convention that you use, stack or caller cleans up, register base, and so forth. So a combination of those should be able to be analysed by the system, reasonably effectively.
For data flow analysis.
Sorry, say that again.
How come you use horn clauses or data log for data flow analysis? Is it more efficient, or was it easier to formulate the queries? So
the data log data flow problem that I represented was basically like a standard definition of a data flow analysis. I used a few different types of data log solvers to do it, and unfortunately, because I had particular ways of representing it, I was limited to the type of data log solvers that I could use, which sort of made it not the best thing. I didn't really follow the path of looking at data log, using it. I originally had the idea that I wanted to use data log exclusively because I thought the data log solution was much better than this sort of complex data flow problem represented as bit vectors. But I implemented that, and I actually got worse times with my data log solver approach to data flow analysis than I got with the bit vector approach. So I sort of stopped looking at that. I think if I did it, if I continue a bit more, I think I'd like to look at the data log approach more, because I think it's a really nice representation of data log problems, and it seems that it has a lot of potential, but in my implementation, I wasn't able to get it fast enough, and it was quite significantly slower as well. But I think, probably the reason for that slowdown was that the transformation from my intermediate representation to the data log, representation is where the slowdown occurs as opposed to the data log solver itself.
Okay, thanks.
I guessed your engine against C++ programs because with all the interaction and whatever, it gets much more complex, I guess.
The question was, have I looked at C++ programs with my engine? Not much, to be honest. I wouldn't say that it would be very good at C++. So C is really the target that I'm looking at the moment. You can certainly pass it binary, C++ binaries, but I wouldn't say that the results will be great.
Apologies if you covered this and I just didn't catch it. What are you doing when you hit a system call in terms of modeling the stack pointer and whether data has been accessed or modified or not?
That's a very good question, actually. What am I doing with system calls in respect to modifying the stack pointer? Currently, what would be happening right now is a bad approximation of that system call. Ideally, if libc is being used or glibc, then you have a reasonable representation. But if you start interspersing system calls, then you'll probably get a bad approximation, and you'll have false positives or false negatives.
So when you were running this on a server, did you ever hit out of memory conditions when your graphs got too big?
Yeah, that's probably like one of the biggest problems with the system. It does tend to use up a lot of memory. My representations that I'm using, I originally designed it with, it's probably better to have a little more in the representation than a little less. So there are limits to what you can scan. As the graphs get bigger, it does get a bit more annoying, and certainly representing the data in the control flow graphs consumes quite a large amount of memory. So there are limitations to how much memory you can get. At the upper end of that graph where I showed ELF binary sizes, there were quite a few times that it ran out of memory. It's a good question. I think the question was, am I running out of memory, the size of the binary or the number of functions in the binaries? What's the relationship between size, versus out of memory? I think as you get more procedures, and also as the graphs get bigger, you start to consume more resources. So if you have really big graphs, big control flow graphs, then it does consume a bit more memory than if you have a few smaller graphs. But yeah, I think ultimately. The only solution I've got at the moment is throwing more memory in the server to do it. So it's not a great solution, but unfortunately it's in relation to my original concept of it's probably better to represent more in the intermediate representation than less. Thank you very much.